Yeah, I'm Harjasleen. I'm here visiting Babis. I was initially hoping for this to be a practice talk for my Asia Group talk in 2-3 weeks now. But then I realized this audience is probably too diverse for that to make a whole lot of sense and be useful to you guys. So I figured I would divvy it into 2 parts. The second part is going to be part of my Asia Group talk. I'm not going to go through all of the technical proof stuff. And the first part, I'll, I guess, motivate that through memory accesses for SNARKs, which I figured is a cute tutorial style talk so that if you haven't seen this before, you can learn something and maybe go implement it later if you want. Okay, so SNARK programming, in general, proof system programming, is a little bit different from regular programming. So in regular programming, for example, you can have if statements. So you have if a condition is true, assign this variable to something, or change the value of this variable y. Otherwise, you do nothing. So if it's true, then you execute this, and then you just go on to other code, right? Now, what happens if it's false? Then you actually just do nothing. You just straight up go to other code, right? You don't have to do anything else. And then basically move on. But the thing is, in SNARK programming, things have to be what is called oblivious. So you can't change what the execution looks like based on the input. And by the way, this is true for like a lot of models of computation. This is true for multi-party computation if you end up working with that as a tool, or in like preventing side channels as well. You basically want to do oblivious computation. So even if you don't want to use SNARKs directly, still kind of interesting model of computation. So what you do is you basically, you do this like condition times what you would do if it's true, plus 1 minus condition times what you would do if it's false. That's how you do if statements, right? So you're essentially always executing everything. Then in regular programming, you can also have while loops that depend on some variable, right? So you break after that many executions, but actually in SNARKs, this is again input dependent, so you can't do this. So what you actually have to end up doing is change it into a for loop and run it for maximum number of variables, have a condition, and then go on from there like we did before, right? So now I said,
well, you can change this, right? You can, instead of doing a for, you can have a jump after the count, right? And the jump would be to an address plus something, and then you can either, right?
But the thing is how many like cycles you execute?
Yeah. The jump could be, let's say, count, right? Count less than you make it into a Boolean, right? Times either the beginning of the loop or other code.
That will end up, it seems nice, but will end up being input dependent now because like whether you execute the loop one more time or you go to other code is dependent on the input now.
Okay.
Right? So yeah, I mean, that's basically what a while loop is doing, right? It's like a jump condition. And same for a for loop, really, if you have a break statement, but you can't have those in SNARKs or any sort of input oblivious type of programming model. Okay, so I have only shown you some random snippets of SNARK programming and peculiarities so far. They're kind of interesting. So what does this have to do with memory? So memory accesses, where do they show up that are like input dependent? Think about like AES, right? When you execute the SBox function of an AES encryption, or using it as a as the SBox for a hash function, it depends what you're reading depends on the input. So just to motivate why this is interesting, right? So you have an array, and which variable you use depends on the input. And now the naive if case of like which variable you're going to use in this array actually quickly becomes unwieldy. But before we see why, let's just quickly talk about the RAM model. So the RAM model is just an abstraction previously used in theory, frequently used in SNARKs, MPC, stuff like that. It has two operations, you read and you write. And each read has a location, which is the location in the memory that you're going to deal with, essentially. And it has value. So for reads, it's the value that was in that location originally. For writes, it's the value being written in that location. Okay, so in addition to that, one other thing you can consider is a time step. So it's basically the index of this operation, so like how many RAM operations you've executed. So an example would be, at time step 0, I read, so I have this array already instantiated, say like somebody wrote it down already, or it comes as part of the program. And then I say read at time step 0, read location 1, and its value is B1. At time step 1, write location 5, and what you're gonna write there, it's 32. At time step 2, do another write, this to location 6. So this is how this like array is mutating. Again, you can keep doing this, and next time you read from location 5, you're gonna read the value that was last written to it. This, by the way, should give you some intuition for like, I'm gonna get to this, but like what invariance is the RAM preserving? It's saying every time you do a read, so when you do a write, it doesn't matter what was there before, but every time you do a read, it must read the most recent value written in that memory block. Okay, so how does this look? In a SNARK, we could do a linear scan. We could say we have a 6 variable array, and you want to read some location and set a variable equal to its value. So how you do this is you have a for loop, you have a condition which says, is this location equal to I? If it is, then I'm gonna increment that variable with whatever the value there is. This should be hopefully pretty intuitive. So same for writes, you basically now, instead of changing the variable, you change the array. So you do stuff to get the variable, then you do this for loop linear scan, essentially. And then in the case, so this is the first technique. This is why this is unwieldy if you do it naively. It's basically always linear in the size of the array.
Is this something you have to do in like common circuit languages, or is it under the hood?
Actually, in many of them, you still have to do this if you want to do RAM model.
Like Circum or
yeah, sometimes you have to. I actually haven't seen any of them very nicely expose their API for doing like more clever RAM model, but that's maybe discussion for later on. But okay, so this is the most naive though. You see that this is linear. If the array is very small, maybe this is actually fine, and any other technique you use is going to have some sort of cryptographic overhead, so there's some crossover point. So, I mean, it's not completely useless, but if you are doing SNARK programming for like small arrays, it's probably fine. But when you get to bigger arrays, if you ever tried programming this, you'll see that it becomes very unwieldy as n grows large. So the second technique is what you can do is you use a Merkle tree. Most frequently people have used Merkle trees for this, but you can use any vector commitment. And what you do is essentially outside of the proof system, you like generate a witness for membership or like opening the location of the vector. And that's how you do a read. And so if this proof verifies, you go on and do whatever you were gonna do, right? Now, what do you do if you want to do a write? You do stuff to get 32, same as before for the writing to 5. You want to write. We also have previous and new commitment to the array and a proof. And we want to set that location to be the value of the variable. So this is what you do. You basically verify the write in the vector commitment, and then you store the newest commitment as your like running commitment. You might be asking, why is there a special operation to verify write? Like, why can't I do something naive and just check 2 membership proofs? Because we already have that tool, right? Why do we need this new one? Does anybody want to think about why that might be the case? Why you need this slightly different tool? Like, what if I just did read the location with respect to the previous commitment and then read it with respect to the new commitment and then just set the new commitment?
What if the right modified something else in the tree?
Exactly. So what if this should also check that nothing else changed? And actually, by the way, there's like a cute property of a lot of common vector commitments, which is that when you give a proof, usually it's like everything, it like commits to everything except for the one thing that you're giving the proof for. And this is true for the membership proof. So actually the cute thing is for Merkle trees, for example, you could, when you give the membership proof, the commitment will change, but the like sibling path is going to be the same in both the old commitment and new commitment, right? If nothing else changed. And by the way, Nusrat, I think, was here some while ago. He has a cool paper about some lower bounds and vector commitments, and they have this like nice definition of like proofs that like commit to the rest of the vector essentially. And pretty much everything we know actually has this property, so that's kind of nice. Do with that what you will, but we're gonna move on. Unless anybody has questions.
Sorry, this is supposed to be better because of the like log and like.
So if you use Merkle tree, then it's log n. If you use some other vector commitment, it might even be constant time.
But this assumes that whatever overhead comes with like doing this verification, which might involve hashing, is still less expensive than doing the linear scan.
That's what I meant with there's a crossover point where the log n, the constants for the log n function become smaller than the constants for the O of n function, which was doing the linear scans, right? So actually for Merkle trees, the crossover point ends up being pretty high, depending on which proof system and which hash function and stuff you're using. We can come back to that when we look at the hash functions a little bit more. The third technique, I intuited this a little bit, is what is called the memory invariant. Now what I'm saying is instead of doing, so the same way that I guess the same way that we had before, you have like every round operation has a time step that comes with it. The invariant is, say I read from location I, the value should match the value that was written there most recently. So how do you do this? Initially, you write all the values. After write and read, you write them all down, increment after every time step, do the rest of the operations this way. Initially you like initialize all the variables like V1 through V6, right? Like we had with these time steps. And then you do the reads and writes as well. So now you have this array L. This is the array of reads and writes. What you do is you compute another array L prime. And this L prime is going to be sorted by memory location first and time step second. So if you notice, this is only sorted by time step, right? That one is sorted by both memory and time step. First location, then time step. Now, let's look at this L prime, right? There's some nice things about it that we're going to see. First thing, if you can check that L prime is a permutation of L, then you know that you haven't deleted any reads or writes. Then you want to make sure that the first thing, I guess, sorry, this is my bad. I've indexed them with 0 before, and now I'm indexing them with 1. But I guess what I'm trying to say is the first position in this L prime array should always be the memory location 1. So you start with the lowest memory location. You don't want to skip any memory location. And you also start with 0 as the time step. Then for every position, in this L prime. If the location changes, then it needs to be incremented by 1. So this is basically slowly building on to checking that I kept every location, I didn't throw anything out, right? Then if the location is the same, so I'm going through this array 1 by 1, I notice the location is the same, then the time step needs to be increasing. So I'm just checking, up until now, I'm just checking the sorting, right? And then if the operation is read, then the previous value should be the same value as it is now. So this is basically checking all of the memory essentially, right? And of course you want to make sure a few housekeeping things, that the timestamp is all valid, and stuff like that. And you will make sure that you cover timestamp 0 to 9 by the permutation check implicitly, right? Because the SNARK is the one that's like giving you the array L. So you okay, sorry. Anybody have questions about this?
If we read a certain value and then we want to write that value that we just read into a different input.
So then we first set it to a variable.
Right.
Then we do the normal write that we would do using that variable.
Okay. Then when we permute the different order of these reads and writes, could that not mess it up because we have to write before we know what variable it is we're reading?
So this L
Yeah.
that you're generating, the like actual things that you're writing in it, here I'm abstracting away how you know those are correct, but you can assume those are correct.
Okay.
And so then the permutation check is maintaining that those two arrays are the same,
Okay.
right? So the first array has already checked that if you read something and wrote it right back somewhere else,
yeah,
that's being done correctly. That's already checked.
Okay.
In building L before you get to L prime.
Right. Okay.
Any other questions? Okay, if not then let's go to the last technique. This is called the read set, write set technique. And basically you're gonna maintain a different set for both the reads and the writes. And every read that you do must correspond to a valid write, is the thing that we're gonna now maintain. And the way that we're gonna maintain this is by, the way that we're gonna maintain this is with a tool, cryptographic way of getting equality of multisets. So like two sets, they might have repeats, you wanna make sure they're equal. Okay, this is not the same as a vector commitment or an accumulator because you can't show, we haven't made the condition that you need to show membership of one specific value. We haven't said you need to show anything about the ordering, that doesn't matter. So somewhat simpler than vector commitments and accumulators in that sense. Does that make sense? So just keep this tool in mind and let's try to see if we can build this read set, write set equality thing, right? So what I have is this array L, and then I write down all the writes in the write set, and I write down all the reads in the read set. And maybe I keep a timestamp only for the writes now, not for the reads anymore. And maybe like initially when I initialize everything, I can just timestamp it at 0 because I don't care about the ordering anymore that much. Right? Or like I care about it when I'm writing down again, but I don't care about the ordering from everything that was written initially. Okay, well, this is not going to be able to use multiset equality, right? Because these are not equal, like very obviously, like for every location that you wrote, if you didn't read it, then like for every, so basically you would need a valid read for every corresponding to every write in order to be able to use this multiset equality. Maybe this will become a little bit clearer. And also there's another problem. What if I just read twice from a location without writing? these sets are not equal now, still, right? So even if I were to try to fill it in with everything else, it's not gonna work. So instead what you do is you write the initial values of everything. And then, we're doing the same operations as before. Whenever you do a read, you also write it back with an updated write timestamp. So first, remember we did a read from location 1, then we did a read from location 5, we write it back. The colors are corresponding, hopefully everybody can mark that. Ask me later if you can't. Then every time you do, every time you do a write, you read first and then you write. So you read the previous entry for that location and then you do a write. Same again, for location 6, I was gonna write. This was like the ordering of the operations. I don't know if there's a lot. So if you don't remember, that's fine. So now I want to do a write first, then I read as well. Again, I want to read location 5. I read it and I write it back without changing it. So in the SNARK, you're making sure that every time you do a read, you just write back with an incremented timestamp. So you increment your timestamp in general. Every time you do a write, you make sure you also inserted something into this read set before you wrote. Okay, so if you make sure, so now I still though cannot use this multi-set equality tool clearly, right? I mean, just look at them. So note that each memory location has exactly one write set value that's never been read. Because initially I wrote everything, and then every time I did a read, I did a write. So it's always going to stay one more write for every location than it has reads. So what you do is at the end you do a finalize step, and the read set basically just reads every location once. And now look at them, they're actually equal. Right? I think there might be a little bug there, but this last one should be 51 and not E6 about that. But they should be equal if I did this correctly. So yeah, do you guys want to stare at this for another second or?
Yeah, that's a quick question. Why does the reader have to read from location 5 3 times?
Because also it wrote to location 5 twice, so it has to read for every write. And then at the end, we're gonna read everything every location once. So that's gonna be the third time that 5 is gonna get read.
And then this last thing happens like no matter what, whether it was read to
Exactly.
before or what.
Because what is it we're maintaining? The write set always has one more entry for every memory location than the read set. So you need to fix that at the end, is what we're trying to do.
If we have to read from every single location at the end, is that not still linear time? So it's not better than like the first technique where we did linear too?
It seems like it, right? But I mean, over time, this cost is going to get amortized away because now if you do 5n reads or 5n RAM operations, that's going to get amortized away. It's just one more of them instead of doing n squared. If I do 5n RAM operations, if I did linear scan, it would be 5n squared, would be the complexity, right? Because every time I did a read, I would do O of n work.
Okay.
Is there a reason you do this like padding at the end instead of the beginning?
Is there a reason to do the padding at the end is basically correcting for the padding at the beginning. But the thing is, the padding at the beginning is just an initialization, like, because you have some initial values for all of your variables.
But I'm saying, why don't you do the like reads that you don't need, those like 6 ones at the beginning? It can at least
Because you might read from the same location again, right?
right, but if you mean the blue, like the colored ones?
Yeah, those colors might happen. Like if you read from location 0, I guess you could do that. Why don't we think about it offline?
That would also account for order.
But you don't need order with this tool specifically.
That was gonna be my second question. So for this multi-set equality, you don't care that you exactly match the value read with the value read.
Not yet.
Okay.
That's going to basically get implicitly checked now, because when you're doing the reads and writes in the SNARK, you're checking that you're adding to the set by essentially always incrementing the time step when you do a write, and always doing a read for whichever location you did a write for. It's not saying it's a correct read yet. It's just saying you're doing a read for the same location. And the timestamp of that read is less than the current timestamp because it was written before. Does that make sense? Actually, to answer your question, I think the reads, the padding can be done before or after for the reads, and it's probably okay either way. Actually, maybe not, because location 1 got actually read and then it got written back. How would you account for like this guy? Because this didn't get written or read again until this finalization step, right? But yeah, I mean, just something to think about for later. Okay, just because I want to make sure we get to the other stuff as well. So again, reminder, you keep a timestamp t increment at each write. No, you can increment it at each op. Even at reads, you increment it, right? Because you write it back. So read and write, they come in pairs. When you read, make sure the value of the read item is less than the current timestamp. Also, write back the read value, the most recent timestamp, and for write, read previous, then add to the write set with the most recent timestamp. So this is just a summary of what we said. And at the end, you do a full scan. And now finally, what you need to do is actually you just need to prove the read set is equal to the write set. And that all of that together is going to prove that the memory operations are all done correctly.
Why we need to use the equality check instead of like the subset check?
Subset check, because I could have, for example, actually, yeah. Why is a subset check not enough? Well, you could do a subset check for the read set being a subset of the write set. But one, I think some of those tools may be more expensive. We'll see the tools that we have to do multi-set equality in a second.
Is that polynomial stuff?
Sorry?
Is that polynomial stuff?
Those tools?
Yeah.
Actually, it's a little bit better even.
Okay.
I will see. Like for every read, it's actually of 1. So, or every read and write is of 1 to do that equality check. Yeah, I mean, I guess it's just that subset checks, they require slightly different tools and they tend to be a bit more heavyweight and just have higher complexity. Probably a subset check would also work. Yeah, that's a good point though. So if you can find a subset check that works better than what I will show you in a little bit, then get you write a paper together. Please take me on your paper.
Yeah.
Okay. So actually, by the way, this you will have to believe me that I showed you the simplest versions of all of these different methods, but there are somewhat updated versions. And based on that, they require, for example, so for setup, actually turns out for these guys, you can get away without doing some setup. For read and write, these two are of 1 each. There is some work at the end, which doesn't have to happen for the first two, but does have to happen for both of these. And so that gives you the total. It's like read set, write set obviously wins out because it's equal to number of locations that get checked. get touched at all. And by the way, this final improvement is due to Özdemir, Alex Özdemir, and others from Dan Bonet's group. So this one is reasonably recent. But this read set, write set technique, by the way, existed for quite a long time in like the memory checking literature for something called offline memory checking, which is I do a bunch of memory operations, I check them at the end. And in memory checking itself, people didn't find it very useful because they're like, well, I have a cloud. Memory checking generally is like, you have a cloud, you outsource your memory to the cloud, you want to make sure it's not tampering with specific memory locations. So how do you make sure about that? Offline memory checking is kind of weird in that setting because you want to make sure every read or write you're doing is correct, right? So there they use mostly online memory checking. Also because only recently have lower bound questions in online memory checking been resolved. Some of them by wonderful folks over here. I'm talking about your locality paper.
The one, oh.
Yeah. But for this like offline memory checking, people knew for a long time OF1 is good. So yeah. So that's where this comes from. So it seems like, you know, everybody should pick this. Let's just go with this. Why are we even wasting our time learning about anything else? There's a drawback here, actually. So existing solutions basically consist of this thing called multiset hashing, like where you hash into a discrete log hard group, and then you add up everything. And by that, you can very efficiently do equality checking, assuming these hashes are not too expensive. But unfortunately, that assumption fails when you're working in SNARKs. Hashing actually can be very expensive. So now we're at the second half of the talk, where I'm gonna try to show you how you can get rid of this drawback. In the meantime, I guess I'll pause for questions here before we move on.
Can you go to the previous slide? Is there something like that's noteworthy here compared to the story you told us so far? Like any of these cells? So it seems that read write is always better than.
Yeah, pretty much. Yeah, so I guess part of what this is born out of is like I spent a bunch of time thinking about RAM model SNARKs. And then I went through the literature, looked at everything that like existed and what the advantages and disadvantages were. And sure, there is like this extra complexity at the end. Like you said, there's like the O of n reading of everything earlier. But it still seemed like it that O of n actually reduces the number of locations touched when you use this optimization. So it seems like it wins out. And actually asymptotically it does win out. Because you don't have to do comparisons in SNARKs. Those can be expensive, especially if you're in what we call arithmetic circuit-based SNARKs. Like comparisons are easy in Boolean circuits, but they're hard in arithmetic circuits. So you get rid of that. You get rid of this, like, everything needs to be initialized, it turns out. With some assumptions and coverages, but yeah.
And just to make sure I understand, these are the costs that go into the circuit that you're building a SNARK.
Exactly. So yeah, this is also not counting for like outside of the SNARK costs. So for example, here you could say like, oh, you're using a Merkle tree. Merkle trees are so terrible. I hate them. What if you used a KZG-based vector commitment, guys? Come on, grow up. But the thing is, then the outside of the SNARK cost grows. That's one disadvantage. The second disadvantage actually is that then you have to do some like actually difficult to analyze and clever matching of like which fields and groups the KZG SNARK exists in, or sorry, the KZG exists in, and which field or group you're doing the actual circuit stuff over, which also ends up being kind of complicated. But yeah, then outside of the SNARK, you're doing O of n work for every read or write witness generation. Make sense? Okay, other questions?
Sorry, could you just clarify where the SNARK lives, like in the setup? Does the SNARK wrap around the whole thing? It's like
Yes.
verifying that everything is done correctly?
Oh, I see that. The SNARK is verifying everything except in this guy.
Yeah.
For the set equality.
Yeah.
So the SNARK is building something like a digest of the set, but it's not showing anything about the equality. You just check that outside of the SNARK. You can check it in the SNARK too, but it's just one comparison outside.
Right.
Then this memory invariant, you basically do the permutation check frequently. You do that outside of the SNARK. Pretty much everything else is in the SNARK. I mean, those permutation checks, by the way, are pretty efficient. You can use like some sort of Fiat-Shamir tricks to make them reasonably good, but yeah. Yeah, and then here, I mean, here this is all in the SNARK. Here the like Merkle proof you provide out from outside the SNARK, and then the SNARK verifies the proof itself.
Right. Okay, that makes sense.
Is that
Yeah.
and then maybe that also clarifies what you're probably confused also about my comment about KCG stuff. Because that is the proof generation is happening outside of the SNARK, the verification is in the SNARK.
For the Merkle tracer, you have to provide like opening proof like for each reader, right?
Exactly.
So those bunch of they're part of the witness, yes, right.
Okay. Anything else? I think I've killed enough time to not have to go to the security proofs for my second part now, so. I guess we could go to these drawbacks. Okay, so this is the drawback. Hashing is expensive in SNARKs. Doing the set equality, this is the typical way that you do it. Hash into an elliptic curve group. One that is D-log hard. And it turns out, and this summation, by the way, is the like group operation. I'm representing it by addition. Yeah. But you can do additive notation, whatever you prefer. So yeah, so now we're gonna talk about our paper, which is the constraint-friendly Map-to-Elliptic-Curve-Group relations. And their applications is in parentheses because I would not talk about any other application. And this joint work with Jens Groth, who's at Nexus, Enol, who's at UC Berkeley, student of Sanjung Berg, and Andrew Miller, who is my advisor. Okay, so maybe we can go back to multi-set hash functions. First, so what are multi-set hash functions? You have some message space M. You have a digest space D. This function takes sets in the message space, so subsets of the message space, and maps them to the digest. Classical construction is this: you take a group, which is D-log hard, like I said, and suppose that this is a function that hashes items in, suppose hash to group, so this is not multi-set hash to group, just hash to group, is a hash function that takes messages and hashes them into the group. Then multi-set hash can just be a sum of the hash to groups, like I showed you. And let me just quickly argue the security for this in the random oracle model. So just classical construction, this is just what I said. So the security is mainly collision resistance, right? So you have two sets, S1 and S2. And you want to show that the probability of finding a collision of their multi-set hashes is very low. So if you do find this, that means that you found the sets such that hash to group, the summation of hash to group over set 1 and the summation of hash to group over the elements of set 2, they subtract to give you 0 in the now you count the multiplicities because remember it's multi-set, so everything could have multiple occurrences. This means that the adversary actually found non-trivial AMs, so that actually the summation over all of the items equals 0. And we don't really want we know that this is actually just the like generalized D-log assumption that this is hard. So it just reduces the hardness of D-log, assuming that the hash function is collision resistant itself. Yeah. So if it breaks the if this is a random oracle, this breaks D-log. And it also has some other nice properties. So one is compression. You just have one group element as the digest of a whole set, right? No matter how long the set is, I mean, within reason for security analysis and stuff. But for the purposes of heuristic, like the digest size is constant, and this is actually incremental, meaning if I have a multi-set hash for a set S, and then I want to compute a multi-set hash for S union T for some other set, you can just add their multi-set hashes and get the multi-set hash for both of them, which is really nice, because now what I can do is, and going back to the reads and writes, every time you do a new read or a new write, you can like add one item to the set, right? So you can basically do a union with a singleton set. So going back to the motivation, so you have the read set and write set. So you have operations. First, you initialize every memory location. This is just 2 memory locations now, so you can see there. Then maybe you want to load location 2 or address 2. You read it and you write it back. Timestamps are increasing. Then you want to store a new value, so you want to write to location 1 with B1 prime. So you do the same thing you did before, you read and you write it back. Load address 1 again, so you're reading again, read and write it back. And then you do some finalizing where you like read both memory locations. You only have 2 right now. Okay, so this was what it looked like, what the sets look like. This is just what we had before. And now what you can do with this multi-set hashing is you can have a digest for the read set, and that's just incrementing. And you have a digest for the write set, which is also incrementing like that. Right? Does this make sense? Where this H is the hash-to-group that I mentioned before. So now the theorem is if the reads and writes are consistent, so they're done properly, then the read set and write set should have the same digest. And that's enough for you to do. Now, first note, these are both multi-set hashes now. Second note, this multi-set hash needs to be computed in the constraint system of the SNARK or proof system that you're working with, right? So that was the thing that I earlier mentioned was kind of bad. By the way, sorry about the repetition. These slides are what I will keep for my Asia Crypt talk. So if you have feedback on the later slides, let me know. So now we would basically want to go to something else. Okay. So now you have G an elliptic curve group. You have some message space. We're going to assume that it's in the field over which the curve group is. By the way, if you've never seen an elliptic curve group, it's just X and Y such that they satisfy that equation up there. And then you have a hash function, so cryptographic hash function, collision resistance, all of those properties, right? And say you have some function that takes items from the field and maps them to the group. So now what you can do is you just say like, oh, first you hash M to get M prime, and then you just do this map to group from the field. And then now in the proof system, you just give it Mx and Y and then verify that this is true. Still, again, this requires computing, so this is in the proof system, you're computing the hash. So I guess this is just elucidating what I said before. But actually hash functions have really high circuit constraint cost. Just to show you, these are all numbers from something called Noir. And so these are basically clock constraints. So our main challenge is, can we remove the cryptographic hash from the circuit while keeping something kind of like hash-to-group, something that kind of has similar properties? So what happens if we don't use an NM oracle? What if we straight away use that function f that I said it takes? Because remember this was kind of weird, right? Because I said this goes from message to the field, and then f goes from field to G. Like, why can't you just use it directly, right? Because message is also in the field already. And this often is the case for SNARKs, right? That something is already in the field. So if you have this, if it's injective, meaning if you have two items A and B in the message space, f of those two items is not equal. Then this is compression. It gives you compression and it gives you incrementality, same as before, right? And also it seems like it gives you collision resistance, right? Because no two items can map to the same thing. You get the same D-log argument as before. So it seems like we're good, we're done, but actually we're not done. There's an issue here. If f is not what we will define in a second properly, inverse excluding, so possible to have two messages that map to points that are inverses of each other, then basically you can have like, you can add up those and get 0, right? Now it's very easy to find sets of items that add up to whatever you need. You just do some extra reads or writes to get that equality. Okay. And so yeah, just to formally define this, if f is a function from the message space to G, and f is inverse excluding if this property is true. And an elliptic curve in Weierstrass form, this is actually the case, is the negative of the curve point is equal to x comma minus y. And what does this minus y in a field even mean? I mean, fields don't have positive or negative. That's why our comparisons were hard, right? But the thing is, it just means that it doesn't have a square root. So based on that, what we say is you have an elliptic curve group. You have a message space, something like this. Sorry, did I mention that f was injective? I think it was on the slide, but maybe I didn't say it out loud. But f has to be injective, so it can't map two items to the same thing. Yeah, that's what injective is. Okay, so this is the message space. So 32 bytes, for example, like 3 32-byte words. So this could be like adder, log, t value, right? Or if you want to have fewer locations, you can have larger values or something like that. You have a tweak space, which right now I just kind of pick arbitrarily. So to compute f of m, what you do is you look for the lowest t. So that's what this procedure is doing. It's looking for the lowest t such that y is not a square, has a square root, so it's not a negative in the field, and that x and y are on the curve. The thing is, you have to now prove that t is the smallest possible value, like this, right? And this has to be part of the proof. Remember, for loops, while loops, those are hard to do in SNARK, so you don't want that. So the idea is, what if you allow something non-deterministic? So now you say the language itself is just messages and points. And this is going to be the relation. P is a point. You just have to check the curve equation for this. X ensures that X is like computed correctly, like we said. That ensures the injectiveness. And by the way, the equation that I showed you before, you can go play with it and see why it's injective. And then you check that Y is a quadratic residue. This is what the whole process looks like. And now in the circuit, what you do is the prover just gives a witness the T and Z, where T is the tweak, the Z is the square root of Y, and you just check this stuff. And we've actually traded a heavy hash-to-curve function for something pretty light. So these are just a few multiplications in the circuit, right? Okay. And then just to demonstrate that this is actually efficient, right on time, I guess. We can come back to those slides if there's a couple of minutes. This is the table. I just expanded it to show how they compare. Map-to-group in SNARK compares to a hash-to-group. So this is just the constraints, the bound constraints. This is the like execution time to like compile the circuit and also build the witnesses and stuff like that. By the way, finding the witnesses sometimes is more or less efficient outside of the SNARK. I don't have a graph to show for that, but because like doing SHA hashing in a regular computer is really fast versus map-to-curve requires like all these other field equations to do. But that's okay, right? Because that's not the thing that we're constrained by this day and age. It's more the SNARK part. And then this is showing you the proving time. For SHA, actually the like number of iterations, as you grew the number of iterations, the circuit size grew so large that Noir line didn't support it anymore, which is 2 to the 23 is like what it supports, I think. Versus map-to-curve. And notice when you go to like really high numbers, what the difference is. This like tiny little sleeping yellow line is where map-to-curve sits, and this is everything else. So yeah, hopefully I've convinced you that map-to-curves are nice, and that this read set, write set paradigm for doing memory and SNARKs is the right way to go, and that you should use map-to-curve with it. Please look at the paper and be a little bit careful, because if the size of the message space are too large, then you might get in trouble. So just look at the analysis a little bit. And that's the end of my talk.
Thanks.
How do you know, like, we want the function to be inverse excluding so that we don't have these trivial relations with negative signs? How do we know that we can't efficiently find a different trivial relation? Let's say like
that would become the D-log problem now.
Okay. Okay, that makes sense.
Right, like, and also actually, by the way, one thing to notice that I thought was kind of cute. If you look at this, and you look at this capital T, what this means is that if you like take two different messages and you subtract these equations for different little k's, you'll find that no two values can map to the same subset. And yeah, and then so then once you're in a subset, yeah, it's hard to find. It's basically D-log.
Wow. Okay.
Yeah.
So in the proof of like proving that your map-to-curve is collision resistant for like the multiset hashing, you have to prove that if you find a collision, then either you break the log or you find the inverse.
Yeah, but actually, well, the thing is, maybe I can even just quickly do this on the whiteboard or blackboard. So you have M1 times T. I'm just going to use T. Plus K1 equals M2 times capital T plus K2. And remember K1 and K2 less than equal to capital T greater than equal to 0, or less than capital T actually exactly. This means that M1 minus M2 times T is equal to K2 minus K1. This is at most capital T minus 1. So the only way that this equation can hold is if this guy is 0. That tells you that it's never going to have, well, the inverse excluding is the square part. But the collision part is this, basically just this cube algebra.
What is T again?
T is the size of the tweak space that we're gonna pick.
Which is usually
In our case, he said it could be like 256, like capital T would just be 256. And that actually works. So I mean, this is more like to avoid a probability that you won't get anything on the curve that has a square.